Welcome to this course on digital and logic systems. In today's world, digital systems are everywhere. We are connected by digital systems, and even in the most remote parts of our country, people are using digital systems of one form or the other. We cannot imagine a world today without digital systems. This course is to introduce you to the design of such systems, the fundamental principles that underline how such systems are designed. In this session, we will provide an overview of the course and what you are expected to know by the end of it. We will discuss digital systems and the important role they play in our lives. And I'll also provide you with a session-by-session overview of what you'll be covering in the course. The key topics we'll cover in this session are: what are digital systems? How do these digital systems differ from the traditional analog systems? I use the term traditional today, but actually it is no longer, analog systems are no longer in use that much, even though we still find them in some unique or specialist areas. But in previous times, analog systems were the order of the day. Then these have been overtaken by digital systems. And then we will discuss why digital systems are important. And of course, we'll look at the organization of the course and a session-by-session overview. There are many books that you can use for this course, but our main reading text will be that of Roth C.H., Fundamentals of Logic Design. There is also a book by Toshi and Mitmar and Morse, Digital Systems, Principles and Applications. And there's quite an interesting book, very easy to read, by Floyd, Digital Fundamentals. So any of these books would do for you. Moreover, there's a lot of information on the design of digital systems that are on the net, which you are free to consult. So, what are digital systems? Most quantities that we come across in nature or see are analog. What do we mean by that? What it means is that these systems or these signals or quantities vary continuously. So, for example, the temperature that you might measure in a day would vary continuously. It doesn't just simply jump from, let's say, 30 degrees to 25 degrees or 35 degrees. You know, it will continuously, gradually change. What it means is that such analog systems can generally handle higher power than digital systems because of the nature of their design. So, an example of an analog system would be one such as that line you've seen. Now, the main difference here you see is that there are points on the graph you are seeing. And these points are what we call the digital points that we sample of the analog signal. So the analog signal is a continuously varying outline that you see on the graph. Digital systems can process, store, and transmit data more efficiently than analog systems can. And there are a number of reasons why. Originally, it was thought that digital systems would be less efficient. However, it was soon realized that we can make them more efficient provided we increase the number of bits that we use to store the data. So, in digital system, we assign discrete values to the points on the continuously varying graph. Digital systems are characterized by binary digits or logic levels. In any digital electronic system, you have two states, and this can be represented by either high or low signals or voltages. And these voltages represent numbers in the binary system. So anything in between the high and the low will be invalid. So we need to be able to say what accounts or what value is a high and what is a low. So for example, you might use a 5 battery volt in your system, Now, is it as precisely 5 volts that accounts for high and 0 for low, or what? If you have a number like 3, the voltage is 3, then what is it? Is it high or is it low? We will say, for example, that something in between, we might say a high will be anything, if 5 volts is the limit, then anything between 4.5 and 5.5 is high. And anything between 0.5 and minus 0.5 is low. Anything in between then becomes an invalid value. In binary systems, a single number is called a bit or a binary digit. A bit can have the value of either a 0 or a 1, depending on if the voltage is high or low. Digital waveforms are different from analog waveforms in many respects. Whilst we see an analog waveform varying continuously, a digital waveform will have discrete highs and lows. So you would see it rising sharply to a high and then falling to a low. As you can see on the diagram, you have a signal that starts at low and then rises to a high very sharply. We call that the leading or the rising edge. And then it maintains that value for a short period of time from T0 to T1. And then it then falls again very sharply. And that falling edge we call a trailing edge. So such a signal as in A is called a positive going pulse. That is going from what? Low to high. And then you can have the signal falling from what? A high to a low. And then the falling or the leading edge is the one that is shown on the left, and then it then rises again, which is called the rising or the trailing edge. So this is how your digital waveforms would look like. Now, is it possible that the signal you saw now is an idealized form, that it's got very sharp edges, rising and falling edges? Is it really possible to have a signal that falls or rises so neatly and nicely? The answer is no. Normally, the pulses that make the digital waveforms do not rise or fall in that manner. They would have something as shown in this diagram, where you can see that it sort of rises gradually to a certain level and then maintains a value, but it oscillates about a point and then it falls again. So you can see that it's not a perfect square or rectangular shape that you have. So how then do you characterize or describe such a signal? So we have what is called such a signal, then we have what is known as its amplitude, the baseline, the rise time, because it takes a definite amount of time for it to rise from low to what? High, as opposed to the ideal case where the signal just rises, instantaneously. And then there's the point where it maintains a level, but you can see that it hasn't got one smooth level that is maintaining, but it oscillates, so it overshoots and then it rings and then droops down a bit before beginning to fall. So normally we measure the pulse around the 50% value. So that we call the pulse width. So you have the rise time, then the fall time. And then again, when it falls, it simply doesn't fall to 0 and maintains it. It again sort of rings or a little bit or oscillates a bit. But so that is a reality. However, for us to be able to describe these pulses in digital systems properly, we need to use the idealized form, which are rectangular pulses that goes over time. So there are a number of things that characterize these pulses. These pulses, because they are idealized, would happen at set times, which we call periodic pulses, because they vary periodically. Yeah. So periodic pulse waveforms are composed of pulses that repeats in fixed interval called a period. So the pulse will repeat itself, at fixed intervals. And the frequency is the rate at which it repeats itself. And this frequency, we measure that in hertz. Now, there's a relation between the period of the pulse and how frequently it repeats itself. So the frequency, we say, is inversely proportional to the period. So frequency f equals to 1 over t, which is a period. In addition, there are a number of things that you need to know. That the pulse will have an amplitude, it will have a duty cycle, which is the ratio of the width of the pulse to the period of the pulse. Now, from here, it means that once you know the period of the pulse, you can easily calculate its frequency. Mostly, you'd come across the terms, maybe your mobile phone is operating at, or your computer operates at, let's say 5 gigahertz or something. I mean, these terms are derived from here. It means that the clock or the signal that controls the timing has got that frequency, that is got a period that is repeating at that frequency. So if you say 5 gigahertz, it means if you divide or you take the inverse value of the period, then it amounts to 5 gigahertz. A hertz is actually a period or a cycle that is 1 per second, every second. So there's a period for you can see, and then there's your amplitude. Crucial to every digital systems are timing diagrams. For you to study digital systems, you need to be able to time them or see how these pulses are working. You need to have a timing of them. Normally, this is done with a clock, and the clock will change repeatedly. It will have a certain cycle of frequency, and all other pulses or signals that come will be measured according to it. So a timing diagram will show you the relationship between different digital waveforms. So let's say that you have 3 signals, A, B, and C, right? And then you have a clock that repeats itself periodically. Now you can then see from the diagram that at time t equal to 0, you have, that's the beginning of it, signal A is rising. Signal B is at low, and signal C is at low. After one period, signal A begins to fall, signal B begins to rise, and signal C maintains its value. So you can see sort of the relationship between the signals A, B, and C. This is useful when you want to do the logical addition or multiplication of various signals, that you see how signals will add up or subtract or multiply with digital systems. So now let's look at how digital systems differ from an analog system. Now you have an analog signal on your left. This is a continuously varying signal, as you can see. Now, in a digital system, what we do is that we sample this analog signal at different points. So on your right, you can see that points are taken on this analog signal, various points, which sort of form the contour of this digital signal. These values then are digitized. So we use specific values to represent them. Now it is these values that we then transmit. So we sample the signal at various points, we pick those values, and these values, which are now numbers, is what we transmit. Yeah? And you can see already the advantages in that, in the sense that you have a value. You can manipulate this value as much as you want, and then you transmit this value. And once you receive this value, you can then reconvert it back, into the original signal. Now, why are digital systems important in our lives? Let's look at that. We know that systems that are based on digital circuits touch all aspects of our lives every day. You can think of many things, your homes, products that you use every day. All of these things, are heavily dependent on digital circuits. So you can think about all the sort of the various type of devices that you use, and you can think about the role that digital signals will play in this. Now, how is this course going to be organized? One, you will have a number of individual assignments that you have to do. This will consist of multiple choice questions. You do a mini project, which you do some presentations in class. There might be a group assignment, and of course, you have your end of semester examination. Now, the allocation of marks for all of these are shown in this table, where 15% goes to your individual work, 10% goes for presentations that you do. If you have a group assignment, that takes 15%, and the written exam will take 60% of the marks. Now, what must you be able to do at the end of this course? You must be able to apply switching theory to the solution of design problems. You must describe how information can be represented using two states, understand the basic operations and laws of Boolean algebra, apply these laws to the manipulation of algebraic expressions, explain the functions of a multiplier, and also be able to explain the operation of the SR and clocked D flip-flops. You must be able to design a minimal two-level or multi-level network of AND and OR gates to realize a given function. You should be able to plot a KARNAUGH map or completely or incompletely specified function of up to 6 variables. You should be able to design a multiple output of NAND or NOR networks, draw timing diagrams, that relate to S and R or D flip-flops. What other competencies must you have? You must be able to differentiate between combinational and sequential circuits. You must be able to perform the conversion from one number system to the other. Simplify expressions using laws of Boolean algebra, prove any theorem using a truth table. Also, given a word description of a desired behavior of a logic network, you should be able to write the output of the network as a function of the input variables. So let's look at each session. What are we going to cover in each session? Session 1 will look at the number systems and codes. Number systems are the basis of any logical system or digital system. So you should be able to understand the binary number systems, its similarity to decimal system, be able to convert from binary to decimal and back forth. You should be able to apply arithmetic operations to binary numbers, determine the ones and twos complement of binary numbers. Ones and twos complements are very important. They would help you to understand how additions are done on the computer. In session 2, we will learn how to express binary numbers in different formats. We will carry out arithmetic operations with signed binary numbers. We'll be able to convert binary numbers and hexadecimal number systems, express decimal numbers in binary coded decimal form, convert between binary systems and gray code, explain how to detect code errors, and discuss the cyclic redundancy checks. Right? So that is what we'll do in session 2. Session 3 will begin to introduce the concept of Boolean algebra. Understand how these basic operations and laws of Boolean algebra work, relate these operations and laws to networks, prove some of these laws or any of these laws, and apply these laws to the manipulation of algebraic expressions. Session 4 will be a continuation of the Boolean algebra. We'll look at how Boolean laws and theorems can be applied to manipulate algebraic expressions. We'll define the exclusive OR. We'll learn how to simplify switching expressions using the laws. We'll learn here that if you're given a word description, how to then change that into a desired logic network. and then be able to write truth tables and write the functions as what is known as min terms and max terms. Section 5 will look at KARNAUGH maps. We should be able to plot a given function, of 3 to 5 variables on a KARNAUGH map. These functions can be either min terms or max terms. Determine the essential prime implicants of a function. Find the prime implicants of a function from a map, and then understand the relation between operations performed using map and the corresponding algebraic operations. In section 6, we'll begin to look at combinational logic design. How do we design a minimal two-level or multi-level circuit of AND and OR gates? How to design or analyze two-level gate circuit using any of the 8 forms of AND, OR, NAND, or OR and NAND, NOR or, and so on. We should be able to design or analyze multi-level NAND gates or NOR gates. Also design a minimal two-level multiple output AND OR and NAND or NOR and NOR circuit using the KARNAUGH maps. Section 7 will be a continuation of combination logics. We'll learn how to do timing diagrams for combination circuit, gate delays, define static zeros and one hazards, dynamic hazards. Given a switching function, how do you realize it using a two-level circuit, which is free of static and dynamic hazards? Design multiple output NAND or NOR circuit using gates with limited fan-ins. Section 8 will be a look at latches and flip-flops. So these are the S and R and D latches. These are very important in the design of memory elements. So how do you store, key question is, how do you store information on a computer or a logic system? So this would help us understand how to retain information in a logic system. Section 9 will look at sequential circuits and then registers. Sequential circuits move away from combinational circuits. Combinational circuits have no memory and cannot remember anything. Sequential circuits, on the other hand, are able to retain information. So we'll explain the operation of these registers, explain the operation of shift registers and how to build them, and then look at the timing diagrams for them. In section 10, which is the final session, we would be looking at analyzing sequential circuits. Analyze a sequential circuit by signal tracing. Given a sequential circuit, you can write the state equations for it, differentiate between a Mealy machine and a Moore machine. Given a state table, construct the corresponding state graph and the reverse. So that's, and then we'll look at finite state machines. We'll touch very briefly on finite state machines. So this sort of brings us to the end of the session. Thanks for listening, and we'll begin by the next session by looking at binary numbers. Thank you.